Dear students, today in this talk I start with intermediate value theorem and then I start uniform continuity. So first start with that intermediate value theorem. So let f closed interval ab to R be a continuous function and say f of a less than f of b. Suppose we have this condition, then for every y such that f of a less than y less than f of b, there exists c belongs to open interval ab such that f of c equal to y. That's mean if fa less than fb, then f attains every values between fa and fb. Now the proof is simple and it is just trivial corollary of the previous theorem which I proved in the last lecture. So first of all, so let g of x equal to f of x minus y. Now since f is continuous on the closed interval ab, therefore g is also continuous on the closed interval ab. Okay. Now what is my g of a? Now g of a will be f of a minus y. Okay. Now we know that f of a less than y, right? So therefore this is less than 0. And what is my g of b? G of b is f of b minus y. Now since f of b bigger than y, therefore f of b minus y, that is g of b, this is bigger than 0. So that is g is a continuous function on the closed interval ab such that ga, gb is strictly less than 0. Right? Thus, by our previous theorem, we have there exists c belongs to open interval ab such that g of c equal to 0, that is f of c equal to y. So we are done, right? So this is one version of intermediate value theorem. Now we can generalize this theorem a little bit and we can write that so again, so let f closed interval ab to R be a continuous function. We have seen that if f is a continuous function on a closed and bounded interval, then f attains its supremum and infimum, right? Now here, so let f equal to supremum of the set f of ab and say small m is the infimum of the set. Okay. Now let m less than equal to r less than equal to capital M. Now then this theorem says there exists c belongs to closed interval ab such that f of c equal to r. That's mean since f is a continuous function on the closed interval ab, therefore f has supremum and infimum, right? Now this theorem says if you choose any value between that supremum and infimum, then f must attain that value at on the domain. Okay. Now this proof is also simple and it is also a corollary of the previous theorem. Previous theorem means the last theorem of our last lecture. So here is the proof. So now if R equal to M or capital M, then we have already seen that proved that there exists C and D belongs to the closed interval AB such that f of C equal to small m and f of D equal to capital M. Right? That's mean f attains is supremum and infimum. Right? So in the last lecture we have proved this. Now suppose m not equal to m and f of say m strictly less than r less than m. Right? Because if r equal to small m or capital M, then we are done. Now assume that small m is not equal to capital M and r is a value between that small m and capital M. Right? Now consider a new function, say g, again closed interval ab to r, defined by g of x equal to f of a minus r. Sorry, f of x minus r. Then obviously by our algebra of continuity, g is continuous on the domain. On the domain AB, right? Now what is my g of c? Now g of c is f of c minus r, and what is f of c? F of c is m, small m minus r, right? So that is less than 0. And what is my g of d? It is f of d minus r, that is capital M minus r, so that is bigger than 0. That is, we have g of c into g of d less than 0, right? Now we have already seen that if g is a continuous function on some closed interval, say cd or dc, depending on c less than d or c is bigger than d, okay? And if we have g of c is less than 0 and g of d is bigger than 0, or their product is less than 0, then there must be a point between c and d such that g of that point is 0, right? So therefore there exists a point, say p belongs to either open interval c or d or d comma c, depending on, we can write here, depending on c less than d or d less than c, okay, such that g of p equal to 0. Now that is f of p equal to r, right? So we are done. Now there is another theorem called the fixed point theorem. This is also very useful to find the root of a function. Now this theorem says so let f be a continuous function from a closed interval AB to closed interval AB. Now note that here domain and codomain both are closed interval AB. Okay, continuous function. Now then this theorem says that function f must have a fixed point. That's mean there exists a c belongs to ab such that f of c equal to c. And here is the proof. This proof is also again simple. So again let g of x equal to f of x minus x. Okay. Now then g, the closed interval ab to r, is a continuous function, right? Since f is continuous and the identity function x is continuous, so g is also continuous on the domain AB. But here the codomain may not be AB, so we write just g is a continuous function from closed interval AB to R. Okay. Now if f of a equal to a or f of b equal to b, then we are done. Right? That's mean then we don't have to anything to prove. Now if f of a not equal to a and f of b is not equal to b, then f of a should be bigger than a and f of b should be less than b, because the codomain of the function is a and b, right? Now then g of a, which is f of a minus a, now that is bigger than 0, and g of b, which is a b minus b, that is less than 0. So therefore g of a into g of b, again their product is less than 0. Now thus, so there exists, say c belongs to open interval ab such that g of c equal to 0. Now what is g of c? Now that imply f of c minus c equal to 0, or that imply f of c equal to c. So we have a fixed point. Fine. Now here in this proof, that closed interval, that in the domain and codomain, that closed and bounded interval is very important. Why? We can see few examples why that closed interval is very important. That is closed and bounded interval. So you can check that if we take f from closed 0 open 1 to closed 0 open 1, and if we define the function f of x equal to x by 2 plus half, then you can check that f does not have any fixed point. Similarly, if we take another example, say f, now this time take open 0 closed 1 to open 0 closed 1, and if we define by f of x equal to x by 2, again you can check that f does not have any fixed point. And if we take example say 3, say f, now open 0 1 to open 0 1. Now again if we take x equal to x by 2, that will also work. Even we can take x square as well. Note that here if we take fx equal to x square, then this is a 1 1 and onto function, right? In fact that is a homeomorphism, but still there is no fixed point. And if you take the closed but unbounded interval, say 0 infinity to 0 infinity, since because of that infinity you can define a function fx equal to say x plus say 1, then again there is no fixed point. Now you can check that the above functions do not have any fixed point. This is the reason that the domain is closed and bounded interval is very important. Now, actually this intermediate value theorem is very important to find a root of a continuous function. We can see one example. So suppose you are asked that prove that the function f from R to R defined by f of x equal to say e to the power x minus 3x square. This has at least 3 real roots. Since the function is not polynomial, so it is actually a difficult problem to find the exact real root. But by using that intermediate value theorem, you can give the existence of 3 real roots. So here is the solution. Now first note that what is the value of e? That is 2 less than e less than 3, right? The values of e is between 2 to 3. Now therefore, what is my f of minus 1? Now f of minus 1 will be 1 by e minus 3, right? Now obviously this is less than 0. Now what is my f of 0? Now f of 0 is e to the power 0, that is 1 minus 0. So this is again bigger than 0. Now what is my f of 1? Now that is e minus 3. Now since e less than 3, so that is less than 0, right? Now if you choose a large number and if you write say f of 8, you can choose any large number, then you will have e to the power 8 minus 3 into 8 square. Why I choose 8 here? Because by my understanding I can see that this is bigger than equal to, or actually bigger than e to the power 8 minus 2 to the power 8. So this is bigger than 0. So you can choose any number. So anyway, so we have f of minus 1 is less than 0, f of 0 is bigger than 0, f of 1 is again less than 0, f of 8 is again bigger than 0. So therefore by intermediate value theorem, there are roots, that's mean f of x equal to 0 in the intervals say 1 is minus 1 0, 0 1 and 1 8. Now since we have 3 such intervals, thus we can see that f has at least 3 real roots. Actually f has exactly 3 real roots, but by the intermediate value theorem you cannot say that f has exactly 3 real roots. But by using that theorem you can say that f has at least 3 real roots. Okay, fine. So this is all about continuity. Now I shall start uniform continuity. Now here is the definition. So let f a to r be a function where a is any non-empty set. Okay. Now f is said to be uniformly continuous on the set A if for every epsilon bigger than 0 there exists delta bigger than 0 such that whenever that mod of x minus y less than delta, that imply f of x minus f of y less than epsilon. Now note that here, so when we define continuity, we define first continuity at a point, right? And then if the function is continuous at each of the point of that domain, then we say that f is continuous on the domain, right? But here for the uniform continuity we shall define directly, so there is no meaning of f is uniformly continuous at a point. So whenever you define uniform continuity, we have to define on the whole domain. Okay. So f is said to be a uniformly continuous on a domain say A if for any epsilon, that is for every epsilon bigger than 0, there exists a delta such that whenever the distance between any 2 points is less than delta, then the distance between f of x and f of y should be less than epsilon. Okay. Now there is one equivalent criteria of this definition. So I can write that criteria as a theorem. So let f a to r be a function where a is any non-empty subset of R. Okay. Now this theorem says then f is uniformly continuous on the domain A if and only if for any two sequences say xn and yn in A such that mod of xn minus yn converts to 0, we have mod of f of xn minus f of yn, that is converges to 0 as n tends to infinity. Okay. So that's mean if we want to show that f is uniformly continuous on a domain A, then it is sufficient to prove that for any two arbitrary sequences xn and yn in A, whenever xn minus yn converts to 0, then f of xn minus f of yn also converts to 0. For a time being, I skip this proof. Okay, so let's see few examples first. So first example, say f of x equal to x square on the domain say open 0 say 7 on this interval. Okay. Now we will prove that f is uniformly continuous or not. So discuss uniform continuity of the function f. Okay. Now first note that what is my f of x minus f of y. Now f of x minus f of y equal to actually x square minus y square, right? Now that is equal to x plus y into x minus y, right? And which is equal to x plus y into x minus y, and then we can write this less than equal to mod x plus mod y mod of x minus y, right? Now that is less than equal to 7 plus 7, say 14 mod of x minus y. So this one. So we have mod of fx minus f of y less than equal to 14 x minus y, this one. Now therefore if xn minus yn that is converts to 0, that imply you can write then mod of f of xn minus f of yn also converts to 0 as n tends to infinity for any two arbitrary sequences xn and yn in the domain 0, 7, right? So therefore f is uniformly continuous. So f is uniformly continuous on the domain, say open 0, open 7, right? Now this is first example. Now if we change the domain, then we can see that f is not uniformly continuous. Here it is another example. This is example 2. Now let the same function fx equal to x square, and we define say in say 0, infinity. Okay, now we change the domain. Now here is the solution. Now we check that actually, so f is not uniformly continuous. Why? So now let xn equal to n plus 1 by n and yn equal to n. Now this is just a trick how to choose this kind of sequence. Now then you can check that mod of xn minus yn, that is just 1 by n, and that is converts to 0 as n tends to infinity, right? But what is my f of xn minus f of yn? Now that is n plus 1 by n whole square minus n square, right? So that is n square plus 2 plus 1 by n square minus n square, which is 2 plus 1 by n square, and that is converts to 2 as n tends to infinity, right? So therefore here we have two sequences such that xn minus yn that converts to 0, but f of xn minus f of yn does not converts to 0. So therefore f is not uniformly continuous on the domain, right? Fine. Now you can see another example. Now let f of x equal to 1 by x and the domain is 0, 1. Now again, we can show that f is not uniformly continuous on the domain. Why? Now let xn equal to say 1 by n plus 1 and yn equal to 1 by n. Now what is my mod of xn minus yn? Now that is 1 by n plus 1 minus 1 by n, which is equal to 1 by n into n plus 1, and that is converts to 0 as n tends to infinity, right? Now what about my mod of f of xn minus f of yn? Now that will be your n plus 1 minus n. So that is 1, right? So that does not converge to 0. So therefore, f is not uniformly continuous on the domain 0, 1. Now you can see another example. Say f of x equal to log x and the domain is 0, 1. Okay. Now again you have to choose two sequences. Now cleverly you can choose some sequences. So now let xn equal to say 1 by n and yn equal to 1 by 2n. Right. Then what is my xn minus yn? That will be 1 by n minus 1 by 2n. So that is just 1 by 2n, right? And that is converts to 0 as n tends to infinity. But what is my mod of f of xn minus f of yn? Now that is log of 1 by n minus log of 1 by 2n. Now that is, if you use the definition or properties of log, then that will be log of 2n by n, right? So that is log 2, right? So that does not converge to 0 as n tends to infinity. So therefore, f is not uniformly continuous on the domain 0, 1. Now I want to state and prove few properties of uniformly continuous function, which will be very helpful to decide that a function is uniformly continuous or not. So first of all, we prove that if f is a uniformly continuous function on a domain say A, then f must be continuous on the domain A as well. That means if you can show that there exists a point on the domain such that f is not continuous at that point, that means f is not uniformly continuous on the domain. Now the next property is, so let f be a function say from A to R and f is uniformly continuous on the domain A. Now if B subset of A, then f is uniformly continuous on B. That means if you can show that f is uniformly continuous on A and B subset of A, then you can easily say that f is uniformly continuous on the domain B. So first of all, it is given that f is uniformly continuous on the domain A, right? And we have to prove that f is continuous on the domain A. Now we first choose a point A belongs to A. And if we can show that f is continuous at A, that's mean f is continuous at each point of A, since A is the arbitrary point, right? Then A will be continuous on the whole domain A. So what we will do, we first choose a sequence yn, which is just a constant sequence. Okay, that is constant A. Now we choose, so let xn be an arbitrary sequence in A such that xn converges to A. Fine. So that's mean xn minus yn, since yn is just the singleton set A, right? So that's mean xn minus yn, that is converts to 0 as n tends to infinity. Now it is given that f is uniformly continuous on the domain, right? Now since f is uniformly continuous on the domain A, therefore mod of f of xn minus f of yn, that is also converts to 0 as n tends to infinity, right? Now what is my f of yn? So each yn is A, right? So that imply mod of f of xn minus f of A, since yn equal to A, so f of yn is f of A, that is converts to 0, right? And that imply f of xn converts to f of A as n tends to infinity. So we have chosen an arbitrary sequence xn such that xn converts to A, and we prove that f of xn converts to f of A, right? So therefore, since the sequence xn is arbitrary, therefore f is continuous at the point A. Now since the point A is arbitrary, thus we can say that f is continuous on the whole domain A. So first choose an epsilon bigger than 0. Okay. Now to prove that f is uniformly continuous on the domain A union B, what we need to prove? So we need to find a delta positive number such that whenever x minus y less than delta and x and y both belongs to A union B, that should imply mod of f of x minus f of y less than epsilon, right? So we need to find such a delta. Here we use the fact that f is uniformly continuous on A and also on B. Okay. So first of all, since f is uniformly continuous on A, so for given say epsilon by 2, there exists a say positive delta 1 bigger than 0 such that whenever x minus y less than delta 1 and xy belongs to a, that imply mod of f of x minus f of y less than epsilon by 2. Okay, this is the definition of uniformly continuous on A. Now similarly, since f is uniformly continuous on B for any positive number, so we choose for epsilon by 2 bigger than 0, there exists say delta 2 bigger than 0 such that whenever mod of x minus y less than delta 2 and x comma y belongs to B, that will imply mod of f of x minus f of y less than epsilon by 2. Fine. Now we choose delta equal to minimum of delta 1 and delta 2. Now we claim that this delta will work for our purpose. So first of all, let x comma y belongs to A union B such that mod of x minus y less than delta, and we claim that mod of f of x minus f of y less than epsilon. Why? So here we have three cases. So first case, if both x and y belongs to A, then we have x minus y that is less than delta 1, right? Since delta equal to minimum of delta 1 and delta 2. Now then mod of f of x minus f of y that is less than epsilon by 2 and which is less than epsilon. So we are done. Now here is the case 2. Now if x comma y belongs to B, right, then mod of x minus y less than delta 2, right, because x minus y less than delta and delta is minimum of delta 1 and delta 2. So this is delta 2 and this implies mod of f of x minus f of y, again this is less than epsilon by 2 and this is less than epsilon. Now there is another case. Now here we can choose one from A and another from B. So without loss we can assume that x belongs to A and y belongs to B. Then we choose some number z belongs to A intersection B, since this is non-empty, such that either x less than equal to z less than equal to y or y less than equal to z less than equal to x, right? It is depending on x less than y or y less than x. Fine. Now since x minus y less than delta, now that imply mod of x minus z that is less than delta, which is less than equal to delta 1, and y minus z that is also less than delta and less than equal to delta 2. Now by the given condition we have f of x minus f of z that is less than epsilon by 2 and f of z minus f of y that is less than epsilon by 2. So thus mod of f of x minus f of z, f of y, that is less than equal to mod of f of x plus minus f of z plus f of z minus f of y, and this is less than epsilon by 2 plus epsilon by 2, which is epsilon, right? So we are done. So in all of these three cases, we have mod of f of x minus f of y less than epsilon. So we are done. So thus f is uniformly continuous on the domain A union B. Now note that if A intersection B is empty, then this theory may not hold. That's mean if A intersection B is empty, then it may happen that F is uniformly continuous on A and uniformly continuous on B, but F is not uniformly continuous on A union B. There is one example we can give. Say f is a function from open interval 0, 1, union 1, 2 to R such that f of x equal to say 1 in the interval, or you can say when x belongs to open interval 0, 1 and say equal to 2 when x belongs to 1, 2. Now note that 1 is not in the domain, right? And f is continuous on the domain 0, 1 and on the domain 1, 2. Thus, f is continuous on the domain 0, 1 union 1, 2, right? But f is not uniformly continuous, because you can check xn equal to say 1 minus 1 by n and say yn equal to 1 plus 1 by n. Now then mod of xn minus yn, that is just 1 by 2n, right? 2 by n, that is converts to 0 as n tending to infinity, right? But mod of f of xn minus f of yn, that is 1 minus 2, that is 1, not tends to 0 as n tends to infinity, right? So therefore f is not uniformly continuous. But you can check that since f is just a constant function on the domain, so f is uniformly continuous on open interval 0, 1 and open interval 0, 2. We can write that as well. But f is uniformly continuous on 0, 1 and on 1, 2. Okay. Now we prove another important property of uniformly continuous function. So let f be a real valued function which is continuous on the closed and bounded interval, say ab. Then we prove that f is uniformly continuous. Okay. Now here is the proof. So we prove this theorem via contradiction. So first of all, assume that f is not uniformly continuous, and we will arrive at contradiction. Okay. Now since f is not uniformly continuous, then there exists epsilon bigger than 0 and two sequences xn and yn in the domain AB such that xn minus yn that converts to 0, but we can write here as n tends to infinity, but mod of f of xn minus f of yn greater equal to epsilon for all n. Why is this true? First, recall the definition of uniform continuity. If f is uniformly continuous on a domain A, that's mean for any two sequences xn and yn in A with xn minus yn converts to 0, we must have f of xn minus f of yn converts to 0 as n tends to infinity, right? But here we assume that f is not uniformly continuous on the domain A. That's mean there exist two sequences in A, say xn and yn in A, such that mod of xn minus yn converts to 0, but f of xn minus yn does not converts to 0. Now what do you mean by f of xn minus yn does not converts to 0? Note that that term is positive. Now since this does not converts to 0 means either mod of f of xn minus f of yn diverges to infinity or it is oscillating. Now if mod of f of xn minus f of yn diverges to infinity, that's mean after some stage all of this number bigger equal to some positive number, right? And it is oscillating, then we always get a subsequence such that say f of xrn minus f of yrn bigger equal to some positive number, say epsilon. Fine. In any case, we can assume that subsequence as my whole sequence. So we can say that there exist two sequences xn and yn such that xn minus yn converts to 0, but f of xn minus f of yn greater equal to epsilon for all n. Fine. Now since xn is a sequence in the closed and bounded interval, so we can say that xn, the sequence xn, is bounded, right? Therefore, by that Bolzano-Weierstrass theorem, xn has a convergent subsequence, say xrn, right? Now let xrn converts to C. Now since we have closed set, that is closed and bounded interval, therefore C must be in the interval AB, right? Because we can write that A less than equal to xrn less than equal to B. Now this is converts to C, that imply A less than equal to C less than equal to B, right? Okay. Now it is given that, or we can write, since xrn converts to C and xrn minus yrn, that is converts to 0 as n tends to infinity, that imply yrn, that is also converts to C, right? Now given that f is continuous on the domain AB, right? Therefore f is continuous at C. Thus by our definition, f of xrn converts to f of C and f of yrn converts to f of C as n tends to infinity, right? Now therefore mod of f of xrn minus f of yrn, that is converts to 0 as n tends to infinity. But by our construction we can check that this one, right? This is true for all n. So but by our construction mod of f of xn minus f of yn, or we can write xrn minus f of yrn, that is greater equal to epsilon for all n, right? So this is a contradiction. Thus we assume that f is not uniformly continuous and we get a contradiction. Therefore f must be uniformly continuous. On the domain closed interval a b, right? Fine. Now by using this one we can solve many problems. So first of all we can see first example. Say f of x equal to sin x by x on the domain 0 1, right? Now check that limit x tending to 0 plus f of x, which is 1, right? Sin x by x, that is 1, and limit x tends to 1 minus f of x, that is also well defined. Therefore we can define the function f at 0 and 1 as well, and we get a continuous function on closed interval 0 1, right? So thus f can be extended continuously on closed interval 0 1. But we have seen that any continuous function on the closed interval 0 1 is also uniformly continuous, right? So since f is continuous on the closed interval 0 1, therefore f is uniformly continuous on the domain as well. Since open interval 0 1 is a subset of closed interval 0 1, therefore f is uniformly continuous on the open interval 0 1 as well. Okay, so we are done. Now here is the second example. Say f of x equal to sin 1 by x on the domain 0 1. Now here check that limit x tends to 1, that is well defined, but if you take limit x tends to 0, then this is not well defined. So we cannot extend this function continuously on the closed interval 0 1, right? Now we will prove that this is not uniformly continuous. So let xn equal to 1 by 2n pi and yn equal to 1 by 2n pi plus pi by 2. Then you can check that xn and yn both converge to 0 as n tends to infinity. That imply mod of xn minus yn, that is also converge to 0 as n tends to infinity, but mod of f of xn minus f of yn, if you find this, that will be sin 2n pi minus sin 2n pi plus pi by 2, that is 0 minus 1, that is always 1, so not converge to 0 as n tends to infinity. Thus f is not uniformly continuous on the domain 0, 1. Okay. Now there is another property. This is simple. You can just check that by your definition. If there exists m, say positive number, such that mod of f of x minus f of y less than m times mod of x minus y for all x, y in some domain A, then f is uniformly continuous on A. Right? This proof is very simple. Easy. Right? If you choose any two arbitrary sequences xn and yn in A such that mod of xn minus yn converges to 0, then by the given condition f of xn minus f of yn, that is also converges to 0. So we are done. So f is uniformly continuous on A. So we can use this fact. So here is my third example. Say f of x equal to root over x on open interval 0 infinity. Now first you check that limit x tends to 0, f of 0 is well defined, right? So here f can be extended continuously on closed interval 0 infinity as limit x tends to 0 plus f of x is well defined, right? Now we know that f is uniformly continuous on closed interval 0, 1, right? Because we know any continuous function on a closed and bounded interval is uniformly continuous, as f is continuous on the closed and bounded interval. Okay. Now we claim that f is uniformly continuous on the interval 1 infinity as well. Why? We can find that f of x minus f of y, what is this? This is root x minus root y. Now if you multiply with root x plus root y on the both side, then you will get x minus y divided by root x plus root y, right? Now since 1 less than equal to root x, so 1 by root x less than equal to 1, so therefore that is less than equal to mod of x minus y less than equal to half into x minus y. So therefore f is uniformly continuous on 1 infinity, right? Here we can write that. So thus f is uniformly continuous on 0 infinity as well, because it is uniformly continuous on the closed interval 0, 1 and the closed interval 1 infinity, and they have a common intersection. Therefore it is uniformly continuous on the union of those two intervals. So it is uniformly continuous on the interval close 0 open infinity, and hence on open 0 infinity, which was my actual domain. Fine. Now there is another one. This is also very interesting one. Say f of x equal to log x on, say, interval a infinity, where a bigger than 0. Okay. Now here you have to use something which we do not know now, but you will see when you know the differentiability. So by the mean value theorem you know this one. So f of x minus f of y by x minus y, that is sum f dash c for some c in the domain a infinity. Okay, since f is differentiable on the domain. So for this you have to prove that it is differentiable on the domain. Now what is my f dash c? That is 1 by c, and that is less than 1 by a. So therefore mod of f of x minus f of y less than 1 by a mod of x minus y. Now since f satisfies this property on this interval, therefore f is uniformly continuous on the interval a infinity. There is another interesting property of uniformly continuous function which can be useful to compute that a function is uniformly continuous or not, and this is the property. So if xn is a Cauchy sequence in A, and if f is a uniformly continuous function on A, then f of xn is also a Cauchy sequence. That's mean if f is a uniformly continuous function, then the image of a Cauchy sequence is also a Cauchy sequence. That's mean if xn is a Cauchy sequence such that f of xn is not a Cauchy sequence, then you can easily say that f is not uniformly continuous on that domain. Okay. So I skipped this proof and I left this one as an exercise. Okay. So I stop here.